Okay, in the last video, we learned a bunch of equations. And those equations were designed to help us find the amount of some reactant at some time t after the reaction started. And we determined the concentration of our reactant using three variables. The amount of the reactant that was present initially, so we designate that by A0, meaning time at time 0 here, the rate constant K, and the time T. And that looks different for the different orders. We have 0th order, we have 1st order, and we have 2nd order. And the way these equations look, for 0 order, the amount that's going to be present at time t, that's going to be the amount that's present initially minus the product of the rate constant and time. And that's it. That's all we got to know for 0th order. Generally speaking, you're not going to see any problems in 0 order kinetics. You will see them in 1st and 2nd order kinetics. And those are going to look like this. We remember for 1st order kinetics, the amount of our reactant present at time t, that's going to be equal to the amount present initially times e to the negative kt. So we take the product of k and t, we take the negative of that, we exponentiate it, e to the power of that, and we multiply it by the initial concentration. For a 2nd order process, it's going to look like this. And your book doesn't give you this equation. I do. The amount that's present at time t, that's going to be equal to the amount present initially divided by this whole sum, which is 1 plus the product of the amount present initially and the rate constant and the time. Now, there are also linear forms of these two equations that your book also gives you. And those linear forms are going to look like this. The natural log of the amount present at time t, that's going to be the natural log of the amount present initially minus kt. So these are your two possible equations that you might want to use for a 1st order decay problem. And the linear form of the 2nd order decay problem, that's going to look like this. The amount present, 1 divided by the amount present at time t, that's going to be 1 divided by the amount present initially plus kt. So this will be the linear form of our 2nd order decay problem. And we'll do two problems, just to give you an idea how this works. We're going to start with this one. Actually, this one has two parts. This is a 1st order decay problem. And this 1st order decay problem reads as follows. And I'm gonna assign these variables as I read through the problem. So there's going to be an AT, maybe that's what I'm looking for. I need to assign an A0, the amount initially. I need to assign the rate constant, and I need to assign the time. All right, let me read through this. We've got a 1st order reaction. We've got our rate constant. There's my K. Here's my K. So I've got that. Check that off. There's K. There's the rate constant. Here's the reaction. They give me the initial concentration of my reactant. Hey, that's A0, isn't it? Sure is. Right there. A0. What's the concentration after 600 seconds? That's my time. So I got this, I got this, I got this. I'm looking for the constant. That's what I'm looking for, right? What is the concentration at 600 seconds is what I'm looking for. So I think this is going to be the best form of the equation to use. I want to find the amount present at time t if I'm given all this stuff. So that should be fairly straightforward. So let's see. Part A, the amount present at 600 seconds. That's going to be the amount present initially, e to the minus kt, which should be equal to, let's see, A naught, there it is, 0.0165 molar, times e to the negative k, which is 4.8, times 10 to the negative 4, inverse seconds, right there, times t, which is 600 seconds. All right, so I'm going to take this product up here. So let's see, 4.8 times 10 to the negative 4. So I'm going to go EE 4, make it negative. So that's 4.8 times 10 to the negative 4. I'm going to multiply that by 600. And if I do that, this product here is 0.288. And notice the units cancel, which it should. Anything that I put in the exponent here, anything that you're exponentiating should be unitless. So the problem now looks like this. The amount present at 600 seconds is going to be 0.0165 molar times e to the negative 0.288. That's that product. So to find e to the negative 0.288, first I'm going to make this negative, and I'm going to hit this button e to the x right there. So e to the power of negative 0.288, hit equal, so that's 0.7, basically 0.75. It's about 75% of that. So I'm going to multiply this, which is basically 0.75 to 2 sig figs. Multiply it by this number, and I get 0.0124, 3 sig figs. I'm going to assume that this time, I'm not sure about this, but I'm going to assume this time is known to the nearest second. That's 3 sig figs. My unit's going to be molar. This unit survives. So I've got a reaction where this is being lost over time, and we start with 0.0165 molar, and look, it drops after 600 seconds. So that kind of makes sense. I would expect this number to be lower than this number. So that, I think I did that okay. Let's do part B. Part B asks, how long is it going to take for the concentration of N2O5 to decrease by 0.01 molar? This is a little tricky. This one's a little tricky. So in this case, we still know A0 and we still know K. We know both of those, right? This is our initial concentration, and I know the rate constant. Those aren't going to change. What I don't know is time. That's what I'm looking for. I'm looking for how long. So I'm looking for time. But what's the amount that's going to be present at time t? Well, it's got to decrease by 0.01. So the amount at time t should be 0.01 less than this. That's kind of tricky. 0.0165 molar minus 0.0100 molar. That's going to give me 0.0065 molar. So yeah, if my concentration decreases by 0.01 molar, this is going to be what's going to be left at the end of this particular experiment. Now in this case, I'm looking for time. Yeah, I am. I'm looking for time. And to do this, I'm going to use this form. I'm going to use a linearized form of the equation. It's just going to be a little bit easier. So if I do that, it's going to look like this. The natural log of what's present at time t equals the natural log of what's present initially minus kt. That's the equation I'm going to use. All right? And I want to get t alone because that's what I'm looking for. So let's see, to get t alone, let's subtract the natural log of a naught from both sides. Well, that'll cancel here. And I'll have the natural log of a at time t minus the natural log of my initial concentration is a negative kt. Yeah, because I've got to subtract the a naught from both sides. When I subtract the a naught from this side, it cancels, but of course, there's nothing to cancel it out over here. Now, if I want time, I'm just going to divide both sides by negative k, and I now have an equation for the time. Natural log of a at time t minus natural log of a initially over k. All right, well, what's that going to be? Natural log of a initially. Oh, I got that backwards. Natural log of a at time t. It almost caught me. That's this value. That's this value. And we're going to subtract the natural log of a initially, which is my 0.0165. And then we're going to divide that by a negative 4.18. This should be a negative k. 4.80, sorry, times 10 to the negative 4 inverse seconds. So my time is going to be, what's the natural log of 0.0065? Hit the natural log button. Negative 5.036. And I'm going to subtract 0.0165. Hit the natural log of that. So subtract a negative 4.104. And I need to divide that by negative 4.8 times 10 to the negative fourth inverse seconds. All right, these units drop anytime you take the natural log of a unit. Those units are going to drop. Now notice there's a tricky thing here. The natural log of this number is a negative number. The natural log of this number is also a negative number, but recognize you're taking this value and you're subtracting this value. So I'm subtracting a negative, which means I have to make it positive. So it's going to end up being 5.036, and that's got to be a negative value. Where is it? Make it negative, yep. And then I got to add 4.104. So in the numerator, I have negative 0.932, and I'm going to divide that by negative 4.8 times 10 to the negative 4 inverse seconds. Well, that's going to go positive, right? Make it positive. So I'm going to divide this by 4.8 EE4, make it negative. 1942 seconds. Why I know that seconds? Because look at your unit here that survives. It's an inverse second on the denominator. Now I better check my sig figs here. It looks like we're going with 3 sig figs. So in order to write this in a way that represents there should be 3 sig figs in the answer, I'm going to write it like this. 1.94 times 10 to the third seconds. Should be how long it's going to take for our concentration to decrease from 0.0165 molar to 0.0065 molar. Notice we decreased to a lower concentration here, so it should take more time. It did. It took more time than 600 seconds, right? It took 600 seconds to get us here, and it looks like it's going to take, almost, I guess another 1,300 seconds to get us the rest of the way. Okay, that's a first order problem. 2 first order problems, actually. Now let's look at this second order problem. This one we've just got some reaction of the form where some reactant A is going to products. We are told it's a second order reaction. We're given here's K, we're given the rate constant K. Liter per mole per second, those units are per molar per second. They gave us our initial concentration, so we have an A naught right here. And they want to know how much time, how many seconds. So we want to know T. And we're given the concentration of A at some time later, right there. 5.5 times 10 to the negative 5th mole per liter. So this is my A at time T. So let's see, if I want time, which form of this equation do I want to use? I think I want to use this one because it's kind of easy to get time alone here, right? Much easier than using this equation. So I'm going to use this one. It's going to look like this. 1 over A at time t equals 1 over A initially plus kt. I'll subtract 1 over A naught from both sides. These cancel. And on this side I have 1 over AT minus 1 over A naught is kt. And now I just got to divide both sides by the rate constant. And that's it. There's my expression for the time. So to find the time, I just got to take the inverse of the amount at time t, subtract that from the inverse of the amount initially, and divide by the rate constant. Let's see if that works. Let's see if the units work out. So t is going to be equal to, let's see, 1 over A at time t, 1 over 5.5 times 10 to the negative 5 molar, minus 1 over 0.159 molar. That's my initial concentration right there, 0.159. And we're going to divide this answer by 0.169 per molar per second. Oh boy, what's this going to be? I'm going to do this one first. 5.5 exponential 5, make it negative, yeah. That's this number here, but I got to take the inverse of it, so I got to go 1 over x. So that's going to be 18,182, and the units there are going to be molar to the minus 1, right? Because that's on the denominator. And then I need to subtract from this 0.159. I got to put that on the denominator, so that's 1 over x. 6.3, again, molar to the minus 1. And I'm going to divide this by 0.169 inverse molar inverse seconds. Well, in the numerator, come on, man, that's pretty much 18,000, but I'll do the calculation anyway. 18,182 minus 6.3. So my numerator, I have 18,176 inverse molar. Getting a little crowded here, I apologize for that. But my time is going to be, right, I calculated this, 18,176 inverse molar, and I need to divide that by 0.169 inverse molar inverse seconds. So I'm going to divide by that, divide by 0.169. Holy cow, that's a long time, man. That is a long time. My time is going to be 107,548 units will be seconds, right? Because the inverse molars cancel. I have an inverse second on the denominator that's going to go to seconds. I need to write this with 3 significant digits because I have two significant digits, right? So this is going to come out to 1.1 times 10 to the, 1, 2, 3, 4, 5 seconds. Oh, that's messy, but that's a wrap.